There's that. This is so weird. I wonder. Like that. There you go. I'm framed up pretty well. It just seems like it's zoomed in on me more sometimes. Test for volume. Test for volume. Okay. I'm getting stuff set up. So we're live, but as it says, stream will actually begin soon. I'll be back in a moment. All right, testing volume.
All right, testing volume. All right.
Volume's working. Testing camera. Camera's working. Oh, I'm a little washed out. Oh, okay, it adjusted. My headband's all askew. Howdy, y'all. We are starting the Sunday chill stream early. I'm going early. I am having a fair bit of success with my new anxiety meds. It's making it easier to focus and things like that. So yeah, I'm going a little bit early. I have stuff to focus on. I have several physics questions to go over today. Physics problems. Yeah. I suppose let's do our introduction, eh? So let's stuff reconnect. There we go. Oh, you can see my cursor. Fantastic. So, as always, we start off saying abolish ICE. Abolish ICE, abolish ICE, abolish ICE. We'll keep saying it until it happens. Impeach Kristi Noem. Get the CBP under control. Ultimately, impeach Trump as well. I just post midterms, we may actually get that, and that would be really amazing. If you're old enough to vote, please make sure you're registered wherever you're currently living. Make sure you're registered to vote, or make sure you'll be able to get your my date is off. Make sure you'll be able to get your ballot. I guess, do they call that an absentee ballot? If you're like away for college or something. And yeah, vote. And you don't have to vote the way I think you should vote. You just should vote, right? Even if you disagree with me. I mean, in some cases, I would even go so far to say, especially if you disagree with me. It's not about. It's about making sure that what most people want is what is represented by our government. And when we only have close to 50% turnout for elections, it skews the elections. It skews them towards the people who are willing to turn out, and a lot of times those are the people with the more extremist beliefs, people with more desire for control over other people. So you turn out to vote and say, I don't desire other people to have control over me. I want to exercise my voice. And right now, my voice is calling to abolish ICE and get them out of our cities, demask them, charge the ICE officers and officials who have committed heinous crimes and have abused their power. That's what we're calling for. Let's do the introduction, shall we? My name's Ryan. I'm the calculus tutor. These streams are where I answer math questions and work through math problems submitted by people out in the world. mostly students who are in math classes, high school, college students. Um, but I'm happy to talk about any math question that gets submitted to me, or questions just about school in general, physics, uh, computer programming, Excel stuff, all of that. You know, if you're not sure, if you have a question about anything in that sphere and you're not sure who to ask, shoot the question to me. So, how do you do that? How do you submit a question to me? Um, well, let me tell you. Off this screen share. So what you saw there, those are the notes. You can get access to those notes, and I'll show you how in just a moment as we're going through this. Oh, hi. I navigated away. So, if you have a math question that you'd like me to answer on stream, um, oh, first I got to make sure that my screen share actually propagates through. Okay, there we go. Go to thecalculustutor.com/live. That's the page you're seeing right now. If you just go to thecalculustutor.com, that's totally fine as well. You're still in the right place. Um, but so this is just the home page. You can see there's a submit a question button right there. There's also a go to notes, and you can go directly to that notes document. You can navigate around. But thecalculustutor.com/live has a little bit is better set up for supporting these live streams. That other page is just my home page, right? So you can see up here, go away keyboard. You can see right here, there's a menu and you can submit math questions. There's also a place to get to those notes, like I showed. And then if you scroll down, you can see that the stream itself is contained right here. There's also a link to submit questions in the description of this video. If you're actually on YouTube itself, if you just go to the video description, you'll probably have to click the expand, read more, or whatever it says. But in there's a link to submit questions, and there's a link to these notes. Another box for the notes. And if you scroll down, here's the section all about submitting questions. You can email your questions directly to me, ryan@thecalculustutor.com. And that's totally fine. However, I do have this question submission form set up to hopefully streamline things and just make it more clear what you ought to submit to help me answer your questions. Notice it just loaded the form right up for me because I'm logged into a Google account. You can submit images on this form, files, and if you do that, Google requires that anybody who submits the form be signed into a Google account. So that's a Google requirement. Either way, if you email me or submit the form, I'll have your email address, and that's kind of where the magic of all of this happens. You don't have to watch the stream live. That's just the space where I work on the questions and work on the problems. And I figure I may as well work on them live. But even if you can't tune in live, after the stream, I will email you a link to the specific spot in the notes and the specific timestamp in the VOD recording of the stream where I answer your question. And so, yeah, you submit your question. If you can tune in live and you can ask clarifying or follow-up questions in the live chat, that's the benefit of watching it live. But if not, you still basically get the same benefit. And then of course you can email me back with follow-up or clarifying questions, of course. This form is pretty self-explanatory. You check the box to say that you understand your email address is being collected. Tell me who you are, just your name, how you'd like me to refer to you on stream when this question was submitted by such and such. That way you know when I'm answering your question. So whatever name you'd prefer me to use. You can also include your pronouns there. That'd be a fine place to do it. Let me know where the question came from, the teacher and the class. Mick Sanderson's Geostats, Professor Smith's Math 251, whatever. Just a small little thing helps me organize the responses and let other people know where the question came from. Because chances are, if you're in the class and you have a question, other people in the class have the same question. Um, then of course, a place for you to actually ask your question. Now, remember, you can attach images, and the idea is that you'll attach an image of the math problem you want me to go over, so you don't need to retype the math problem. This is for you to be just a little bit more specific. Like your question could be, "Can you show me how to do this math problem?" And I'm happy, and that's what I'm going to do on the stream is I'm going to work through the math problem. But if you have a more specific question, uh, how do I deal with the fractions in this problem? What do I do if I don't know how to take the derivative of this type of function, um how do I take the derivative of this type of function, whatever. So the more specific question you ask, the more specific help I can give. But regardless, I'm going to go through the problem and try to address what I assume are like the misunderstand or the sticking points or whatever. I'm going to try to give the best advice I can. But if you ask a specific question, I'll know specifically how to help, right? So that's the idea there is you ask your question, um, and it can just be, can you work through this problem, please? That's totally fine. But if you have a more specific question, you can ask it there. Um, and then we're gonna skip this box really quick for just a second. We'll come back to it. But then attach images. So my thinking is if your problem is in a textbook or on a worksheet, just take a picture of the whole page and send it to me. If the question is on it's kind of a long question, it's on two different pages, just take a picture of both pages or take a picture of both sides of the worksheet or whatever, and just send that along to me. If it's online, so if it's web work or my open math or something like that, just take a screenshot and that's totally fine. Take multiple screenshots if the questions is too big to be contained on a single screen. Just send me the whole question is the idea. um if it's in a if like if your teacher posted like a PDF packet type thing to like Canvas or whatever, you can just download that whole PDF and attach the entire PDF. Um, if that's the case, though, you want to be really specific when it says, what is your question? Like, you want to be specific here and tell me, especially if it's in like if you send me multiple pages, tell me, page three, uh, number 15, right? Or number 15 through 18 if there's like a set of problems that you're not sure how to do. Because I'll work through multiple problems just to, you know, show additional stuff. Um, yeah. So if you're going to send me the whole page or send me a whole PDF packet, just be really specific here about which question or which problem or set of problems you want me to work through. Because if you send me a whole page from your textbook or the picture of your whole worksheet, I'm not going to work through the whole worksheet. Um, I mean, I could, but let me know where you specifically want me to focus, right? And then the other thing you might include with these images is a picture of any work you've already done on the problem. Maybe you started the problem and got stuck. Maybe you finished the problem but got the incorrect answer. Uh, maybe it's a problem you all went over in class and you copy down all the work from the board that the teacher did, but you have no idea what's going on. Um, or you kind of understand what's going on. Regardless, if you send me a picture of any work related to that problem, even just notes you took from class about that type of problem, even if it's not about the specific problem that you're asking about, that really helps me kind of understand where you're at, understand your context a little better, and I can give even better advice and help when I'm going over the problem. That's where this box up here comes in. My promise to you is if you send me a picture of your work, it won't show up on stream. Um, why then do I ask permission to show it? I'm not actually asking permission. What this is a place for at higher levels of math, really long problems that have lots of steps and sub-steps and stuff like that. If somebody is looking for help with something like that, sometimes the help they need is for me to go through their math work line by line, go through their whole problem solving process. That's for those people, so they can let me know. Yeah, go ahead and it's you know even though you generally promise not to show people's math work on stream, I need you to go through my work line by line, and therefore I need to see it. It needs to show up on stream, right? So for the most part, you can ignore this. If you don't, I'm basically telling you don't check that box unless you realize you need to check that box. And I would assume those students know who they are. Um, yeah, that's it. That's how you do this. Um, and again, like I said, you can just send your questions directly to me, Ryan at thecalculustutor.com, if that's easier for you. Everything that I asked for in the form is what you should include. Um, you can still take a picture and attach it to your email. I recommend you fill out the form on your phone because then the pictures you take probably with your phone, right, are right there. You don't have to figure out how to like access the pictures from your computer or whatever. And yeah, and once I get your questions, I will answer them. I will work through the problems and answer your questions on the very next live stream. And if I start getting lots of questions, like right now I'm streaming 3 days a week. Uh, or if I start getting lots of questions and I just need more time, I'll add more streams. Or if you say you email me your question or you send me your question on a Wednesday evening after my Wednesday stream, well, I'm not streaming again until Sunday, but you're like, but I need to turn this work in on Friday. If you let me know that when you submit your problem, that you're like, hey, I need help with this and I need to turn it in on Friday, um, I will either do a special stream or I will work on those problems well, I don't want to work on an off stream because I want you to be able to see me. So I will do like a special stream. If it's really imperative that you get them back quick. Um, so yeah, if I can, right? No, that's not a guarantee that I'll be able to do that, but oftentimes I could fit in an extra hour stream sometime, Thursday or Friday most weeks. Um, yeah. So yeah, I mentioned at the top I've got new anxiety meds that are helping me a lot. I think I mentioned on my last stream that our cat has been sick, but she's feeling a fair bit better. We've got some antibiotics for her. We've got a new food for her, and she's doing pretty well. So yeah, I think it's a good day to jump in and do some math. So let return our screen share back to the notes. There we go. Um, s- Stream won't begin shortly. Stream has begun now. Boom. There we go. Um, oh, I need to be on my Miro board so it updates. Ba, ba, ba. Okay, I think we're ready to go. Mm, not quite, not quite. I want to open my calculator emulator. I've been trying to, uh, when relevant, I've been trying to work through these problems on a TI-84, um, so I can demonstrate how to do that with the type of tool that's probably allowed in your math or physics class. Um, Hold on. I think this might be slow because of the screen share. I'm gonna stop sharing really for a moment. Um, I should have ultimately opened this up before I started the stream. Um, there we go. There we go. Boom, boom. Perfect. And of course, it opened two instances. What? Okay, there we go. Excellent. Okay, so I have that open. I can use that when I need to. But for now, oops. For now, let's go back to the notes. Okay, sorry about the clunkiness there. Let's grab the first question. think I'll just do this. Excellent. All right. So this is from a Physics 251 class. This is online work. Professor Ben Farr at University of Oregon is where these questions. Well, I mean that might not be where these questions originate. Teachers steal um, homework questions from all over the place. Um, Regardless, though, that is where the student who submitted these questions got them from, is from their math or their Physics 251 class from Professor Ben Farr. Okay, cool. All right, let's see what we got going on. This is a pretty classic problem. Two blocks are connected by a massless ideal rope. Classic, as shown in the diagram. The mass of the block on the or the mass of the block on the table has mass m. Okay, so mass m1, and the suspended block has mass m2. Very good. Table is frictionless. Interesting. And the pulley is both massless and frictionless. So all we care about is the rope, which is an ideal rope, which means it doesn't stretch or anything like that, and we don't have to worry about the rope's mass, and the masses. Enter an expression for the magnitude of the acceleration of the two connected blocks in terms of the variables given in the problem statement, and use g for the acceleration due to gravity. Okay, so what we want to do here is we want to set up a honestly, the answer should just be G, I think, because this is frictionless. It's not going to resist. There's basically zero resistance to the pull here. And because the rope isn't going to stretch, they both have to accelerate at the same rate. Yeah. So this is pretty straightforward. Mass m1. Oh wait, actually, is no friction. Mass m1 offers or provides no resistance to mass m2. That's my initial thinking. Interesting, though. That would mean the rope would provide no tension. So okay, let's actually go through this instead. Okay, so that's my initial thinking. I think it's always a good idea to sort of at least in your head go through your initial thoughts with a problem. But let's actually look at this the way I'm sure the professor expects you to look at it. Okay. So we're gonna do two free body diagrams. This is mass M1. Oops, let me put the M1. It has a gravity force, right, which is just m times g, or m1 times g, but we'll just say force. Or yeah, we'll say m1 times g. There's also a normal force um, going up, which has to perfectly resist that. So that's also m1 times g. It's not move. M1 is not moving up or down, right? And then it also has a tension force pulling to the right. Okay, cool. Then if we look separately, here is mass 2, the one that's hanging. It has m2 times g is the force pulling down on it. And it has a tension force going up, which has to be the same tension force. So we can use the same. The tension in a rope is constant all the way through in an ideal massless rope like this. Okay. That would kind of have to make the tension 0, but the tension can't be 0 because this gets pulled. Oh, I see. Hold on a sec. Hold on a sec. Hold on a sec. Essentially, what's going to happen is the rope's going to sort of transmit the force, right? This gets pulled down with a force of m2g. Oh, okay. I see what we got to do here. Um, So on this one, we have the sum of forces on the second mass. And we're just talking vertical. Right, is T minus M2G. And then over here, horizontal, the sum of the forces on mass 1 in the horizontal direction is literally just T, positive T to the right. Right? And so this one, and again, because, so Newton's second law, right? Says the sum of the forces equals mass times acceleration. So for this one then, put that over there, make it blue. This is Newton's second law, is something you should definitely just know. Nope, go away, go away. Okay, there we go. Blue, thick. Okay, so we have this. Newton's second law, we're gonna just put that right up there. Okay, yeah, we'll just put it right there. We'll grab these and move them over just a tad. Okay, which means, which means, for this one, um, that T, which is the sum of the forces, has to equal m1 times acceleration. And now notice in the diagram, it says acceleration 1 and acceleration 2, but because they're connected with this ideal rope, um, they have to have the same acceleration. The rope can't stretch. Um, and neither can it compress, really. So there's no way this one is going to go faster and it can't possibly go slower. So we have this. Now, um, we can come over here and we can do the same thing. And in fact, let me line these up. Let's just put those right there. And we'll say that. Okay, so we'll say there. And that means T minus m2g has to equal m2 times the acceleration. We can because so we have a T here and it has to be the same T here, right? Tension has to be the same on both sides of the rope. So here's what we'll do. We will add this m2g to both sides like that. It'll cancel out there. And then so over here, we'll get T is equal to m2a plus m2g, like such. Ba, ba, ba. Oh, I just realized we need to consider our trying to think of the best way to explain this. Because we have sort of a rotation here, and it's the mass on the table is moving to the right, but the mass on the free hanging mass is moving down. We sort of need to make this sort of clockwise direction our positive direction because they're sort of both moving in the same direction, right? Um, Sort of around this pulley. Because yeah, I'm worried about these being one being positive and one being negative. Let's keep going, shall we? Now we see that these are both T. So we can take this and take this, and we can say, okay, M1A has to equal M2A plus M2G. And what we want to do is we want to solve for A. So we subtract the M2A, subtract the M2A, right? Those will cancel out. Over here, we get M1A minus M2A equals M2G. We're going to factor out the A here. So we get A is equal to M1 minus M2, the difference between the masses, M2G. And now we can just simply divide. And we have that the acceleration that these blocks undergo is equal to the force on the second block, which is the force that's causing the movement, divided by the difference between their masses. Notice this on the bottom is going to be a mass, and it will, whatever that mass is, it will cancel out with this mass, leaving us with just essentially some fraction of g. um, or some multiple of g. It's going to be a fraction. It's going to be a partial fraction. Like it, it won't accelerate faster than. Um, and yeah, part of the reason for this is if that block on the table is heavy enough, even without friction, uh, there's this idea of momentum. There won't be enough force to get the object moving. Um, that's one of Newton's other laws: is an object at rest wants to stay at rest until acted upon by an outside force. And actually, without fraction, it would still move, but it would just be very, very slow because the relative if mass 2 is really small compared to mass 1, then the little bit of force that gravity is creating on M2 is only going to move this one very, very slowly. And so what it comes down to, I guess that's a good way to think about this is, okay, we know how much force is generated here. Kind of, we have to take into account the tension, which which counteracts that force a little bit. But then we have to say, okay, based on that force being applied, how fast would this one move? This is the one that ultimately has the impact on the overall acceleration. But yeah, there we go. So this is our. So yeah, we can say M2G divided by M1 minus M2. And there we go. Fantastic. Okay. There's more to this problem, though. Da, 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 da. All right. So enter an expression for the magnitude of the tension in the rope in terms of the variables given in the problem statement. Use G for okay. Um, Since we know what the acceleration is, so we know t is equal to m1a, and from there we know a is equal to m2g over m1 minus m2. So we should just be able to take this, plug it in there, right? Take this, plug it in there. And so we get the tension. Honestly, I feel like you could probably just enter this. But it's okay. Ha. Expression for the magnitude in terms of the variables given in the problem statement. So the only variables given in the problem statement are the masses in g. That's why we can't use this one, because acceleration is not a given value. So we'll do m1 times m2g over m1 minus m2, and m1 times, this is just m1 over 1, right? So this just becomes t equals m1 m2 g over m1 minus m2. There we go. And this is a process in a lot of problems like this, right? Is you set up equations, you use those equations in conjunction. You're like solving systems of equations, right? So you might remember back from like algebra 2 or something like that, solving systems of equations, and it just seemed like kind of arbitrarily hard math problems, maybe for the sake of it. It wasn't. In real life, there's often more than one equation at play, and that doesn't make it more challenging. That actually makes it possible to solve, right? If we didn't have multiple equations to like set this one equal to this one, we couldn't do this sort of algebra. All right. Excellent. That was pretty straightforward. Let's do whoop. All right, part C here. Enter an expression for the speed at which the suspended mass hits the floor if it begins from rest. Give your answer in terms of the acceleration and the distance it travels to reach the floor, D. Ah, okay. Well, for this, we're just going to need one of our kinematic equations, right? Which is just how distance or displacement relates to velocity, relates to speed, or sorry, it relates to acceleration. Um, and we don't know. We want the speed, the velocity. We don't know how long it's going to take. So we need something that has velocity and acceleration and distance, but that doesn't include time. So that is going to be, I think that's going to be our v squared. Yeah, that's going to be our v squared, or sorry, not v, that it is v squared, but v final squared is equal to v initial squared plus 2 times acceleration times the change in displacement. So VF is the speed after a distance delta S. VI is equal to 0, starts from rest, and A, as we know, is equal to M2G, right? Yeah, M2G, sorry about that. M2G over M1 minus M2. Excellent. So we get VF squared is equal to 0 squared plus 2 times M2G over M1 minus M2 times, sorry, I forgot. We have one more piece. Delta S is just equal to that D value it gave us right there. And then so we have a D at the end. And then we don't want this squared, so we'll get rid of the 0. We'll pull the 2 and the D up into the numerator here. Or actually, maybe I'll pull the, yeah. So we'll make this look like the final velocity after it travels a distance D is the square root of 2D M2G all over M1 minus M2. There we go. Right? That's what this is all about. Just putting the equations together. Not bad at all. Cool. We've got another one here. Oops. Of course. Another kind of classic one. Okay. A contestant in a winter sporting event pulls an M kilogram block of ice across a frozen lake by applying a force F at an angle theta, theta above the horizontal, and we can see here. assume that the coefficient of static friction for ice on ice, sorry about that, is 0.03, and the coefficient of kinetic friction for the same. Oh, sorry, that's static friction, and the coefficient for kinetic friction is that 0.01. Let to the right be positive x, and up be the positive y direction. So they're giving us a frame of reference, right? They're telling us positive, positive, like that. Okay. So this is a screenshot from an online homework. It says use the interactive area below to draw a free body diagram to represent the situation where the contestant is pulling, but the block has not yet started to move. Use Fs for the force of static friction and Fk for the force of kinetic friction if they are needed for your free body diagram. Okay, so first thing we're going to do, and so this is a free body diagram of the ice, right? We're not actually worried about the person. They're just the source of force. So here's our ice. There is a force downward, which is going to be the mass of the block times the force of gravity. There is a normal force, which is also actually there is a normal force here, and so one of the things we have to be aware of when we're drawing free body diagrams is the length of the arrows indicate the magnitude or relative magnitudes of the forces that they represent. And because this person is partially pulling up on the ice, they're reducing how much force gravity is pulling the ice into the ground ice on, which means the normal force is going to be reduced. So our gravity force should be longer. Mg. And we'll make a note. Mg is greater than N. There we go. Okay. Then we also have I suppose they don't want us to divide the force of the puller into components. So we're just going to do this. We don't know how long this force is. And we'll label it theta. And then there's a friction force right here. And if it hasn't started moving yet, so static friction, if you haven't started learning about this yet, or you're just starting to and you're not really sure about it, friction comes from the fact that there's no such thing as a perfectly smooth surface, right? Just by its very nature, all surfaces are made of atoms, and atoms can at the very least atoms connect in sort of these sort of crystalline, and there's like lots of geometry, but even at a slightly more macro scale, surfaces have crags and stuff like that. And so what happens is, imagine this is horizontal, right? It's hard for me to do it horizontal, but like imagine my knuckles are one surface and my other knuckles are another surface. When something's set down, it sort of settles into that other surface. And so it takes more force to pull it up out of there. But if it's already moving, it doesn't fall as far down into those cracks as it's moving. And so getting something to start moving from rest, there is a bigger force of friction exerts a higher resistive force. But if something's already moving, then friction still exerts a force, but it's less. So static friction is when something is static, not moving. Kinetic friction is when something is, and you'll learn more about the word kinetic when you learn about kinetic energy and stuff like that. But kinetic just means moving, means motion. Um, so yeah, so this is because it isn't moving yet. This is Fs going straight back. Friction always acts uh, perpendicular, parallel to the surface that is causing the friction. That it always acts parallel to the interface between the two objects. And there we go. That's our free body diagram. We also uh, know F, the force F that the person is exerting. I'll put that right here as a little note. Actually, let's put them to the side. Okay. Notes on force magnitudes, which is to say arrow lengths. So mg, that arrow, has to be greater than the normal force, or the normal force has to be smaller. The force F has to be it's hard to tell. The x component, the horizontal component of this, has to be less than this if it's not moving yet. So I would say maybe we can just summarize that as Fs has to be greater than force F. There we go. I think is because if it's not moving yet, that means the person hasn't overcome the static friction. So the force they're exerting isn't enough. It's technically it's just the x component of this that has to be less than this, but if the whole force is less than that, then its x component is less. So that's probably the easiest way to do it. There we go. Free body diagram. Excellent. Let's keep going, shall we? Okay. Please use draw a free body diagram to represent the situation where the contestant is pulling and the block has just begun to accelerate. Use Fs for the force of static friction, Fk for the force of kinetic friction. Okay, so very, very similar, right? We have mg, we have a slightly smaller normal force. We have our force of the person pulling. Oh my gosh. Which is at an angle theta. And then we still have our friction force. But now it's kinetic friction because it's started moving. The person has overcome the static friction, pulled its block out of its resting place, given it motion, and now friction's still resisting it, but what am I trying to say? But it is moving, so the force of the pull must be greater than the force of the friction, because that's forward motion. Okay, so notes on force magnitudes, which is to say, again, arrow lengths. Again, mg needs to be longer than the normal force. And now here, though, F, the x component of F technically, but F needs to be greater than Fk. Nice. Yeah, because I can't actually see the tool. I have seen it a little bit when I've been the student that submitted this, I work with them one-on-one as well. And I've seen this free body diagram tool like once, but it gives them options to use for the forces, and I don't know what options it gave, so I probably should have had them expand this so I could actually have looked at it before I copied it, but I was just trying to grab them real quick at the end of our session. Okay. Actually, what I can do here, make this easier, is just get rid of that. There we go. Boop. Okay, cool. And now I can attach this. Very good. All right. New question here. You push a block of mass M against a rough vertical wall, applying a horizontal force, perfectly horizontal force. The coefficients of static and kinetic friction between the block and the wall are mu s and mu k, which is just mu is just our variable, our typical variable for coefficient of friction. Gravity acts downward as usual. That's nice. In terms of these variables, mg and whichever u is relevant, what is the minimum force you need to apply to keep the block from sliding? Figure out an equation for F. Okay. So because we don't want the block to slide, so we are concerned with static friction. The equation for friction is always just your coefficient of friction of whatever variety times the normal force. In our diagram, so here, let's draw a free body diagram. Here's our mass M. It's being pulled down with a force of m times g. So they're using capital M. It's being pushed against the wall with this force F that we don't know anything about. And anytime an object is pushed against another object, this is again one of Newton's laws, right? For any force, there's an equal and opposite reactive force. When we're talking about surfaces interfacing, we call that a normal force. So the normal force here is pointed to the left. And so notice what we have. So gravity is down, but we also have, so this is our block M. Actually here, I'm going to draw it as a block. Sorry about that, y'all. m. So we have m times g, we have F, we have the reactive normal force, and then of course we have the force of static friction, which needs to perfectly resist. So to resist motion, vertical forces must be balanced. So force of static friction has to equal m times g. Well, we know what the force of static friction is. It's just that mu s times the normal force, which is mg. But we also know horizontal forces are also balanced. So N has to equal that F, right? And so now we'll take this, bring it down here, and we get mu F is equal to mg. And now we can solve for the F, and we get F has to equal the weight of the object, right? Mass times gravity, that's just what weight is, divided by the coefficient of static friction. And here you have kind of a universal law. Assuming there's nothing else happening, assuming there's no vertical force to resist gravity, you just have a horizontal force pressing something into a rough surface. The force necessary, is just the weight of the object divided by the coefficient of friction between between the object and the surface. And because these coefficients of friction are less than 1, this actually ends up being a multiplier. So you actually have to apply more force than the weight. So if it weighed 1 Newton, you would have to probably apply a couple newtons of force, right? Which I think kind of makes sense since you're not directly opposing it, right? You're pressing it into the object in order to increase that friction force. So hopefully that feels a little intuitive. Yeah, I think we got it. Okay, so there's that. So that's it for all of those. Oh no. No. It's not been doing my screen. Oh my god, I am so sorry, y'all. At some point I switched my screen share and I didn't check to make sure. Oh, that is rough. Okay, well, you can go back and listen to my explanation and look at the notes. I do apologize. Oh, I hate that it does that. When I switch my screen share source, I have to go back and like tap on the stream to get it to actually like show that's so frustrating. And it's probably been doing that for a while since I started working on these. Ugh, I'm so sorry. Well, um, no worries at all, I guess. We'll just keep moving along. Now there is we have some other problems. So this is written homework. This is the written homework from that same class. Actually, hold on. Here's how I want to do this. Grab the whole thing. I want to try to model these. Oops. That's too big. Okay. So I want to try to model the process here. Okay. So we read the whole problem, all the questions that are being asked. So we know what's ahead of us. And so we can sort of understand. And we might realize, oh, it's actually more useful to do part D before we do part B, things like that. Anyway, okay. Oh yeah, I remember this. These problems are titled. I love it. A block slows down. Apparently, this scenario was discussed in class. Okay, a block of mass m is being pulled by a rope with a constant applied force F. The block is sliding on a surface. The coefficient of static friction is mu s. Kinetic friction is mu k. You're used to that. Okay, so they actually give us some details for these values. They give us the mass, 10 kilograms, static, coefficient of static friction is 0.3, kinetic friction 0.1, and the force being applied is 40 newtons. Explain why this force is sufficient to make the block move. Also, what's the minimum F below which the block wouldn't move? Okay, so we want to, given these numbers, we want to examine how the friction force sort of works and stuff like that. Okay, then if we're going to have the block start at rest, I guess we're assuming that we are still using that 40 Newton force. And we want to find its speed after 2 seconds. They want us to draw a force diagram, then set it up with symbols, and then plug in the numbers. That's always our process, though, so that'll be fine. Then after it's gone for 2 seconds, the rope will break. Describe what happens, and then and describe what forces are acting on the block. Okay. How far does the block slide before stopping? Hint, what is VT after the rope breaks? How long does it take until V equals 0? Oh, excuse me. Okay. So that's everything we need to do. I'm gonna crop this to just the problem description, and we're gonna give ourselves a diagram here, right? So we have a block. It has a mass of m. It's being pulled on a surface, right? It doesn't say what angle the force is at, so I think we have to just assume the force is perfectly horizontal, or essentially they're just giving us the horizontal force. There's also friction. Actually, I'll call friction F mu, right? Because it's either kinetic or it's static. Either way, friction opposes the pulling force. Um, it's also being pulled down, m times g, which means it has a normal force, which is also going to be m times g. Okay, so there's that. Now let's look at that first problem, or the first question rather. There we go. Okay, so we have that. Explain why this force is sufficient to make the block move. Also, what's the minimum F below which the block wouldn't move? Okay, so the block will move if the applied force F is greater than the force of static friction, right? So we know we need F to be greater than Fs. Well, we know the force of static friction is just mu s times n. So this is, which is mu s times mg, because n equals mg, right? It's not moving up or down, so the upward force has to equal the downward force. All right, and so we can say that this is 0.3 coefficient of friction is unitless, times 10 kilograms times 9.8 meters per second squared, which is going to equal 0.3 times 10 is just 3, times 9.8 is 29.4, and that'll be newtons. Kilogram meters per second squared, that's a newton. All right, so the minimum force necessary to get the block moving is 29.4 newtons. Um, 40 newtons is greater and will therefore move the block. There we go. Right? We know how to calculate the force of friction. It's a very easy formula. We know how to figure out normal force. It's just the resultant force from whatever other vertical forces are either pushing the object into the table or resisting gravity, reducing how firmly it pushes into the table. Yeah. So there we go. Okay, let's keep going, shall we? Let's grab the next problem. Oh my gosh. Okay. The block starts at rest. So Vi is equal to 0. What is its speed at 2 seconds? First draw force diagram. So, okay, yeah. So they have a particular order they want us to do this in. So I'm gonna get rid of that for right now. So here's our block. It's being pushed this way by a force. It's being resisted this way now by kinetic friction. Because that force of 40 newtons overcame the static friction, it starts moving, and now it has that lower friction um, that it has to overcome. And it's not moving up or down, but we do know there's a normal force. It has a weight, mg. We know the normal force is just equal to that mg. Boom. So the net force, so the sum of our forces, so if we look horizontal, which is the direction it's moving, the sum of forces equals mass times acceleration. In our case, it's going to be capital M mass. We need to find the acceleration to figure out how quickly it's gaining speed, and then we just apply that acceleration for 2 seconds, right? And once we see that, well, we'll go into that more. So our sum of forces, F is in the positive, and actually let's give ourselves a little frame of reference. To the right will be positive, up will be positive, right? So this F, the applied force, is positive, and we'll subtract off the force of friction, right? We're just getting the net force. And that will still equal M times A. We will substitute for the force of friction for the mu times N, which is mg. And we'll also, so yeah, let's do that first. So this will be F equals, oh, not equals, minus, sorry, minus N times mu K equals MA. This is mass times gravity. Mu K equals MA. And now we can just divide by the M. Remember, we have to divide everything by M here, so these M's won't actually cancel out, or at least won't fully cancel out. You can cancel it out here, but then you still have to divide the force by M. So I think it's easier to just write it like this. And so what we end up with is the applied force minus the weight times the coefficient of kinetic friction, all divided by the mass, and that equals our acceleration. So this is why we don't want to plug the numbers in first. We can look at this and make sure we're getting all of the pieces where they actually truly belong. So the algebra process ends up actually being really important. And now what I want to demonstrate is using the TI calculator to actually calculate this in a way that's fluid and simple and accurate. And I say simple as it can be with the TI, which is a really old piece of technology at this point, right? Um, so stop that share. We'll come back here. I'm going to share just my entire screen. Oh, I have to select it. There we go. And then we'll go back to that and we'll pull up the calculator. Boom. There we go. Okay. So I can't get the calculator to stay on top. So we need the force. And actually here, I'm just going to write these numbers down so I can reference them, right? So we know that our F is 40 newtons. We know our mass is here. I'm just going to pull it up on my other screen here. 10 kilograms. We know our mu k is probably 0.1. Yeah, 0.1. Oh, and of course we know our, here, that looks like an m sub g. Let me make that a little bigger. mg. And we know our g is, of course, 9.8 meters per second squared. Yeah. So now what I'm going to do is in the calculator here, I'm going to turn it on. First of all, hello. There it goes. Okay. So we're going to input all of these variables first. So we're going to do 40, and we're going to hit this STO button. That's store a variable. We're going to store that, and I hit alpha to use all the letters that are here. So green alpha gives you the green function of the key. So alpha, we'll hit this because that's our F. Oops. What? Oops. Okay, hold on. 40, store, alpha. Okay, alpha, and then cosine. And so that's what we're telling the calculator is take the number 40 and store that in the variable F. And then anytime we use F from here on out, it'll use 40 until we put something else in F. And we hit enter, and it says 40. That's just what it does. And we'll do the same thing for the mass. 10, we store that. We'll go ahead and store that in M. There isn't a mu, so I'm just going to use K. So 0.1, store that in K. And then finally 9.8, store that in G. There we go. Okay, all of our variables are stored. So now that our variables are stored, no, don't do that. You know what would be really awesome is if you would cooperate. There we go. Hey, there we go. Okay, and now what I want, oh, I see. Anytime I move it, it wants to shrink again. That's totally fine. Okay, and now what I want to do is I want to type in this equation. So something to keep in mind when you're dealing with equations that are fractions, everything in the numerator needs to be in a set of parentheses. And then everything in the denominator does too, but if there's only one thing in the denominator, you don't actually have to put the parentheses. It's only if there's multiple things. So we're going to do parentheses, oops. Parentheses, alpha F, and so we're just typing the variables because the variables are already stored in the calculator. Minus alpha m. And you don't have to write times. It understands if you put the variables beside each other that you're multiplying. So f g, oops. If you hit clear, it clears the whole line. But if you cursor back and highlight the thing and hit delete, it'll delete just that thing. There isn't a backspace button, unfortunately. Okay, M, and then what do we need? G, and then we need K. There we go. And then we can close our parentheses, and then divided by, and then we'll do M again. And there we go. And now if we hit enter, it does the entire calculation for us. Right? So we don't have to mess with making sure we type the numbers in right, or we can check that we type the numbers in right by looking at what's stored in our variables, right? And there we go. So here, in fact, what I'm going to do is is this? Wow, that's annoying. It's not letting me take a screenshot. And of course, it's taking my start menu forever to open. I just wanted to take a screenshot. Do you have a built-in screenshot? No. Maybe, actually. Hold on. Screenshot. Aha. Quick screenshot. All right, but there isn't a good way to paste it. Oh, and I just realized that my calculator is behind my video feed there. Sorry about that. Because I wanted to put this in there into the notes to make it clear that this was just done using a that's annoying. That's real annoying. Oops, wrong button. Edit. There isn't just a paste option. Why don't you just have a paste button? I can go grab another mouse. I just don't want to have a secondary mouse for what I'm doing here. It used to, if I tapped with my finger, it used to bring up a like a little context menu, and oftentimes the only thing in it was paste, but now it doesn't want to do that for some reason. Ooh, I know what I can do though. This is, of course, turn it on. There we go. This is so wonky. Um, I'm going to use the fact that I can see my feed. Excellent. Okay, and then we there we go. Okay. Sorry about the delay while I sort of figured out my technology, y'all. But we got it. Okay. So, in fact, we'll put all of these over here, put this over here, and now we can say, okay, so now we know that, so from here, we can say the block, accelerates at 3.02 meters per second squared. So after 2 seconds, the block will have reached a velocity of 6.04 meters per second. How did I get there? Every second, it's gaining 3.02 meters per second in velocity. And if it does that for 2 seconds, 3.02, and another 3.02 is 6.04. There we go. And then we can say, whoop, that's our answer. And there we go. Very, very good. All right. That's not the end of this. There's a couple more pieces to this problem. So at that 2 second mark, the rope breaks. There we go. The rope breaks. First in words, describe what happens. What forces are acting on the block now? So if the rope breaks, the only horizontal force acting on the block will be friction, which will slow the block until it stops. Of course, there's still gravity and a normal force acting on it, but I think it's pretty clear we're only concerned with, but we can say uh, gravity and the normal force continue to act on the block vertically. Sure, we can say that. Because I have my video feed down in the corner, and sometimes some of the stuff I'm writing gets a little obscured by it. That's a good reason to, if you're following along, even if you're watching this as a VOD, it might be good to just pull up the notes, so you can scroll around and look wherever you want and see stuff that might be for just a moment hidden behind my video feed. All right. And now that we know that it's going to slow down, they want us to figure out how far it moves in that time. So at t equals 2 seconds, VI equals 6.04 meters per second. The friction force, the kinetic friction force, is still times n, which is this times m times g, as friction is the only force, we can find the acceleration. So the sum of forces is equal to mass times acceleration, but the sum of forces here, this is just the negative kinetic force of kinetic friction, right? Which is negative because it's going to the left. The block's moving to the right, which we said is our positive direction. So this is negative mu k mg equals ma. So if we solve for solve for a, notice the mass cancels out, which is kind of interesting. And we just get negative mu k times g is equal to a. Okay, cool. That seems good to know. How long does it take until v equals 0? Okay, so we need to use a kinematic equation. We're looking for time. We have acceleration. Um, we don't really care about how far it goes, so we don't really care about displacement. So we could use that V final is equal to V initial plus A times T, right? We know that V final is going to equal 0. We know that V initial is going to equal 6.04 meters per second. We know that A is equal to negative mu k times g. There we go. So we just want to plug. So we'll plug stuff in. We'll solve for. Actually, here we're not going to write this down yet. We'll get it all figured out. We'll get it solved for t, and then we'll figure out what all our variables equal. So we'll say, oh, okay. So here's this. We'll plug this in for this, and we get VF equals VI minus mu k g times t. Now we want to solve for t. So we can subtract the VI minus VI. That'll go away. So we'll get VF minus VI is equal to negative mu k gt, and we will divide by the negative mu k g divided by mu k g right there. And so we get, we get that t is equal to the change in velocity, Vf minus Vi, over that coefficient of kinetic friction times gravity. That's the downward acceleration that's causing the friction. And there we go. And now from here, we can say, okay, we can type in, we can figure out everything we know, right? We can say, okay, the final velocity is actually 0. The initial velocity is 6.04 meters per second. Mu k is equal to 0.1, and g, of course, is equal to 9.8 meters per second squared. Excellent. And then what we can do is we can go back to our calculator. Our k is already in memory. Our g is already in memory. So what we need is we need a final velocity and an initial velocity. So I'm going to call let's put our initial velocity in. So we'll do 6.04. We're going to store that. We're going to store that in just v, right? Oh, this is a thing I mentioned before, is when you're doing this, it can be helpful to type next to your variables what you're calling them in your calculator. We're calling this v, we're calling this k, we're calling this capital G. This, we can't use v again, and we're already using an f in the, we could override the f since we don't need that force. We could override it, but rather I'm just going to call it w. Right? So, okay. So there's that. So 0. And also keep in mind, since VF is 0, we could just ignore it and make this a negative VI. That would be totally fine. but I like the idea of typing our entire equation in and not worrying what the values are. Typing the values in to the variables and then typing the full equation into the calculator so you can make sure you're typing it in correctly. Um, so I'm going to call this W because it's kind of like a V. Um, and there we go. And so the equation we want to uh, put in the calculator, and you can even write this out as well, right? The thing you're going to type into the calculator is going to be a parenthesis, a W minus V, another parenthesis divided by parenthesis KG, another parenthesis, right? So into calculator, boom. Here, I want to let's write this a little better. So we're gonna so how do I want to do this? So this is all of this is gonna uh, into calculator. No, I'm sorry. I'm trying to figure out how I want to organize these notes. I'm getting caught up on my organization. So right here we'll just say into calculator. It will look like what we're going to type in is parenthesis W minus V parenthesis divided by parenthesis K G close parenthesis, right? Doing this sort of planning, it seems like extra steps, but it really does ultimately save you time. And it seems like extra steps and it seems slow when you're not practiced at it. But once you're practiced at it, it just becomes a little bit second nature once you know how to use your tools. W minus V divided by, and I put parentheses around both the numerator and denominator because there's multiple things in each. K G. Nope. Go back, hit delete. There we go. G. And then hit enter. Oh, oops. You know what I did? I forgot a negative. I forgot a negative right there, which means this should be negative right there, which means we should have a negative right here. Okay, cool. This is actually a good opportunity to so here's how I realized that something was off. I got a negative answer for time. That doesn't make sense, right? And now the number is correct. 6.16 is the right amount of seconds, but because I got a negative, I'm like, something's off, which means maybe the number isn't correct. So you go back and you double check. And notice all I did is I put the negative here, but when I divided on this side, I dropped the negative. It's such a common mistake to make. It's like one of the most common errors. So here's how we correct it really easily in the calculator without having to type everything back in. If you cursor up to that line and hit enter, right? Boom, we can go up. And I believe if I, yeah, and I got rid of that previous, so I cursored up, I hit enter to bring it back down to where I can edit it because you can only edit the bottom line. But I cursored back up and hit clear and got rid of that that incorrect line. And now here's what I'm going to do. I'm going to go over here, but highlight the K. And so these calculators work the way an old school computer terminal works. And it's going to, whatever I type right here, it's going to put in this spot and it's going to push everything else to the right. So I want a negative sign there. Oh, wait, no, it's not. Sorry. Hold on, let's get our k back. Okay. It's not. It's going to overwrite it. What we need to do is we need to do this insert. We could just retype the whole thing. I'm just trying to show you different ways to use your calculator, right? So this insert, so I'm going to hit second, and I'm going to hit that delete. And now because it's see how the cursor changed? If it's an underline cursor, that's the insert. And so whatever I type here, it's going to insert it there and push everything else to the right. Boom. And now I have my negative sign, so I can hit enter. 6.16, but it's positive, which we know it should be, right? Time, where time is moving forward, negative time would mean before the rope snapped. Excellent. There we go. Here, let's take a screenshot of that and put it into the thing. And there we go, into calculator. So we can say, right, that was time, and the question was actually asking how far does the block slide? Oh, there's two questions here. How long does it take until v equals 0, and how far does the block slide before stopping? Ugh, okay. So this is our, okay. So the block slides for 6.16 seconds before stopping. Okay. Actually, here's how I want to do this. Let's just do it this way. So from here, we're going to say, okay, cool. So this is t equals 6.16 seconds. We want to know how far it goes. We can just use another kinematic equation. Oops. To find distance traveled, use a kinematic equation. Right, we just want to use we'll use S equals SI plus V initial T, plus 1/2 AT squared. But this is using this T we calculated. We could also use, actually, hold on a sec. We can use this one. We can use VF squared equals VI squared plus 2A delta S. And we'll recall, right, that A is just equal to, what's it equal to? Negative UKG. UKG negative. Oh my gosh, let's write this a little more nicely, shall we? Equals a negative, right? So this is going to be so VF squared equals VI squared plus, I'm going to say minus 2 mu K G delta S. And now we want to solve for delta S So we'll just subtract the VI squared, subtract VI squared. Oh, those don't cancel out, huh? So we get the difference in the squares of the velocities, squared negative, oh, what's happening? 2 mu k g delta S, and so we will then divide by this. Boop. And so we get that delta S is equal to final velocity squared minus initial velocity squared divided by negative 2 mu k g. But into the calculator, what we're going to type in, right, is going to be parenthesis. We said v final is v and v final is w. So we're going to get w squared minus v squared divided by, and in parentheses, negative 2k g, like that, right? We already have all of these, all of the values we need are already in memory in the calculator, stored in these variables. So we can just type that in if we bring our calculator back up, right? So we can do w squared minus v squared, close our parentheses, divided by, open more parentheses, negative 2. Be really careful. If you're familiar with, if you use TIs, you probably don't need this reminder, but if you haven't really used many TIs very much, there's a negative button that's different than the subtraction, right? If you put a minus, like an actual subtraction symbol there, it'll throw an error because it's like you can't subtract 2 from nothing because it, right. So you have to use a minus. But anyway, minus 2 k g, and then close parentheses and hit enter. And there we go. That seems pretty far, but the speed is pretty high, and it's going to take, it'll keep sliding for 6 seconds, right? And at its original velocity, if it had kept up that velocity when the rope snapped, for 6 seconds, it would have traveled 36 meters in 6 seconds, but it's only traveling 18. So that kind of makes sense. But yeah, think about the numbers you get and think about whether they make sense or not. And if they don't make physical sense, it does mean something might have gone wrong in your calculation, or yeah, you might have accidentally typed in the wrong number for one of your variables or something. All right, and so we can call this delta S equals 18.61 meters. All right, and so we can say, if we go back and look at what the problem was actually asking, this is always what you want to do. How far does the block slide before stopping? How long does it take until v equals 0? Okay. And so we can say the block slides a distance of 18.61 meters after the rope snaps, it takes what did we say? 6.16 seconds for the block to come to rest. On written homework assignments like this, like on those other problems I was doing that were like online homework where you just have to enter the answer, you don't need to write your answer as a sentence. I would encourage you to, at least in your head, say the answer as a sentence, or say out loud, say the answer as a sentence. But on these written homework problems, you absolutely should, after you do all of your work, you should absolutely should restate your answer as a complete sentence. Or in this case, two complete sentences, because there are two questions, right? There we go. Oh, okay. Mm. We are uh, okay. I think I have one more in me. Let's look at the next one. Okay. Two sliding blocks. This is another classic problem. Blocks on a inclined plane. Two the two plot. Let's try that again. The two blocks with different masses and different coefficients of friction, as shown below, are sliding down the incline. What is the tension in the string in terms of the coefficients of friction, gravity, the masses, and the angle? As always, start with force diagrams, one for each block. You'll end up with equations for each block that you can then combine. As always, there isn't some magical formula to remember. It's Newton's laws, the nature of friction, and careful thinking. Hint one, the answer is somewhat ugly. Yeah, that happens a lot. Hint two, what should the answer be in the limiting case? Where they are equal, where the masses are equal to each other. What about 90 degrees? Hint three, it gives us some things. You should find that t equals this. Oh, that's really nice. So once we've come up with an equation, right? Once we've come up with an expression or an equation for the tension in this string, it gives us some values that we can plug in and a result, so we can check our answer. That's really nice. I love that's real great. Okay, so here's our diagram. So here's what we're gonna do. I'm gonna do um, I'm gonna do block one. Zoop. Okay, so block one. Uh, Actually, here I need to lower this down. Block one, and we're going to try to just do like a really typical free body diagram here, right? Where we don't have anything extraneous. We know gravity is pulling it down, so that's m1 times g. That's that force. We also know that there is a normal force here at an angle, right? That angle is just theta from the vertical, right? Um, ba, 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 right? It would be because, oops, just lock that in place there. There we go. Um, and actually here, let's I want to explain that just a little bit. If you have, so we have some sort of inclined plane, we have something here. We know this angle is theta, right? Perpendicular to that, right? Um, right. So this angle is also theta. Um, if we were to continue this down like this, um, yeah. So just geometrically using corresponding angles and things like that, it would have to be that this angle is the same as the angle here measured from the vertical. That's something you can just remember, or you can just draw a diagram for yourself to try to figure out the geometry of it. Um, and if that's something that stumps, or not stumps, but if that just doesn't feel intuitive, that's totally a question I can answer. Like if somebody wants to like ask me, like, can you please like really explain how, like when you're dealing with an angle, how show why the angle is from the vertical. Yeah. Um. Anyway. Ba, ba, ba. Okay. Okay. So we have our normal force because the normal force is always perpendicular to the surface, right? Um. Okay. And then we also have a friction force. Are sliding down the incline. So it is kinetic. Oh, they only give us a kinetic friction. Yeah. So we have uh kinetic friction 1. Um this is normal force 1, I guess we could call it. And then we also have, and then so this is this is also our angle theta. And then of course we have what's pulling it down is the tension, and that is also at an angle theta. Cool. That's it. Um, then we can do same thing for block 2, right? So we got this. We have M2G pulling it down. We have the normal force for block 2, so normal 2. Um, which again is from the horizontal, or sorry, from the vertical there. Um, there's and then there's a tension force pulling back on it, and also a friction force, right? So the tension is here, pulling it back up. Um, and then there's the force of friction also pulling it backwards. Um, so what we can do here that's going to make this easier And it may seem counterintuitive that this is going to make it easier because it might seem like we're like adding complication. Um, we know what direction this is going to move. It's going to move at that angle, right? And so if we can change our frame of reference, so what we're going to try to do, right, is change frame of reference to the angle of incline. And all that means is because like if we tilt our heads at the angle of the incline, now all of a sudden things are just moving left, right, up and down. Right? Gravity is still acting at this sort of weird wonky angle, but we can use trig to split it into down the incline and into the surface, right? So what we're going to do is we're actually going to so I'm going to redraw these diagrams here. In still comes out. FK1 still goes that direction. T still goes that direction, but now also there's gravity pulling it down in that direction, and which is so there's two forces here. There's T, and then there's also mg, and now we have to think. So what is the angle here, or rather, if I draw a line here, right? We have a right angle, and this angle right here. This is our theta. Right? Should seem obvious there. And what we want is we want just this component that's sort of opposite. So SOHCAHTOA tells us sine is the opposite. So this is mg sine theta. And then we also have a force pulling it into the incline, into the surface, and that's going to be mg cosine theta. Okay, and we want to do the same thing over here for this one. We have our normal force coming up. We have our tension force going there, and we have our force of kinetic friction. Oh, this is 2, this is 1. The T aren't T1 and T2 because remember, the tension is the same all through the rope. And that's the thing that sort of is going to unite this whole problem. And then again, there is this mg sine theta going down the incline and mg cosine theta pulling it into the and this should be m1 m1. This should be m2 m2, right? Excellent. Okay, so now we can this just means split gravity into parallel and perpendicular to the incline. There we go. So that's what we did. We split gravity up so that it's going in the same direction. I just want to make it clear that these are both going this way. Excellent. And so we know, let's see. And ultimately what we're looking for, let's go back and look. We are looking for the tension in the string in terms of these coefficients of friction, gravity, the mass, and the angle. So we can, what we want to do is from here, right, we know the tensions have to be equal to each other. Um, so we want to look parallel to incline. So for block 1, right, sum of forces equals mass times acceleration. Mass 1 times the acceleration. And so the sum of forces, that's going to be F. Oh, we need to give ourselves a frame of reference. This is plus, and this is plus. Down the incline is what we're going to call plus. So that makes the forces of friction negative, and we usually want the friction to be negative. It's resisting the motion. It doesn't matter. We can make up the ramp positive and it will all still work out the same. We might get a negative sign someplace that seems wonky, but okay. So on this one, we have the tension plus m1g sine theta. It's going to be, hold on a sec. I just want to make sure it's actually going to be. Yeah, it has to be. Those are parallel. Yeah. Yeah. Sorry. I was checking my trig. Those are the forces down. And then we want to subtract off the force of friction for that one. And that's going to equal mass 1 times acceleration. Okay. Excellent. Let's do block 2. Sum of the forces. So parallel to the incline is mass 2 times this acceleration. They have to have the same acceleration, right? Because the rope is not stretching or compressing. That's going to be critical here. And so our sum of forces here is just m2g sine theta, and then we're subtracting both the tension and the force of friction, and that'll equal m2a. Right? Then what we're going to do is we're going to solve both for A. So solve both for A. So we divide by A. Oh, we don't want to divide by A. We're solving for A. So divide by M1. Divide by M1. So those will cancel out. Divide by M2. 2. So over here, we get that A is equal to T plus M1G sine theta minus FK1 all over M1. And over here, we get that A is equal to M2G sine theta minus the tension minus this one's force of friction all over M2. And now, set them equal to each other, right? They're both equal to A. So this one has to equal this one. So we get that T plus M1G sine theta minus force of friction for the first one over M1 is equal to M2 G sine theta minus tension minus force of friction for the second one over M2. And now we solve for T. Okay. So what we're going to solve for T is we're going to multiply this side by M1 to cancel that out. So we multiply this side by M1. We're going to multiply this side by M2 to cancel those out, which means multiply this side by M2. And we're going to distribute that. That should be an F. So we get, so here, let me write it out though, just so. So we get, oh, and this is supposed to be a T. So we get M2 times T plus M1 G sine theta minus the force of friction on the first one is equal to M1 times M2 G sine theta minus T minus the force of friction on the second one. All right, notice we got rid of the fractions. That's all we were doing in that last step is we were getting rid of the fractions, multiplying both sides by both of the denominators. Now we want to go ahead and distribute this into here and distribute this into here. And so we end up with M2T plus M2 M1 G sine theta minus M2 F K1 equals M1 M2 G sine theta minus M1 T minus M1 F K2. Excellent. Now we want to get the T's together, right? So we're going to add M1T to both sides plus M1T. And at the same time, we're going to get rid of all of this other stuff. So we're going to subtract M2 M1 G sine theta plus M2 F K1. So that'll all cancel out here. But over here, we'll do minus M2 M1 G g sine theta plus m2 fk1. Notice though, m2 m1 m1 m2 g sine theta, these are the same. This is actually going to cancel out there. It's going to cancel out on both sides. We had the same we had the same term on both sides. So we actually get to cancel it out. So over on the left-hand side, we have m1t plus m2t. And over here, this canceled out, this canceled out. So all we have left is m2 times the friction of the first block minus m1 times the friction of the second block. Sort of interesting. M2 times the force of friction for the other, right? Because their forces of friction affect each other. And now here, we're just going to factor out the t, and we just get the sum of the masses, which it sort of makes sense. At some point, we would need the total mass that's involved here. Notice we can't factor out the force of friction here because it's two different forces of friction. And then finally, well, not quite finally, we're almost there. We divide by m1 plus m2. Those will cancel out. We divide by the sum of the masses, right? Okay, and we're pretty close. So we have mass 2 times force of friction on 1 minus m1 times force of friction on 2 divided by the sum of the masses, like that, right? And now here's the thing. Replace FKs with, so actually here's what I want to say is we'll say, remember, Fk is equal to mu k times n, and n is equal to mg cosine theta. So if we come back up to our diagram, right, our normal force is the only thing opposing it, and it's only moving up or down the incline. It's not moving off of it or into it, right? And so those forces those perpendicular forces have to be balanced. So n1 equals m1g cosine theta, n2 equals m2g cosine theta. And so that's what we get down here. And I waited until then to do that so that I didn't have to carry around all of this other stuff during all of this algebra, right? I knew we had the force of friction, and it was just nice and packaged up as Fk. And so what we get then is Fk is equal to mu k mg cosine theta. And so that's what we want to do now is we want to plug. So now expand Fk1 and Fk2. So T is going to equal M2 times mu K1, right? Because this is the force of friction on the first one, times M1 times cosine theta. Then we're going to subtract from that M1 times mu k2, because there's a force of friction on the second one, times m2. Also, oh, we need a g in there. Oh my gosh, I'm so sorry. Okay, hold on. Mu k1 times m1 times g times cosine theta minus m1 times mu k2 m2 g cosine theta, all divided by m1 plus m2. And it did say it was going to be ugly, but I want to point something out. Notice that these two things are nearly identical except for their mu k's. We have an m1 and m2, a g and a cosine all being multiplied. So we can actually factor that out and make this a little bit simpler, right? I'm going to factor out, and because this is a fraction, I'm going to throw it all in the front. And so what we get is we get m1, m2, g cosine theta, all of that. That's everything these have in common. They both have an m1 and an m2. They both have a g, and they both have a cosine theta. And then what's left in the fraction up here, it's just mu k1 minus mu k2. So it's the difference in the coefficients of friction divided by the sum of the masses. And there we go. That should be and now we can check it. We could do this. We could do this in the TI, but it's gonna be a little slow. It's gonna be a little tedious, right? So I'm actually gonna do it on my Desmos calculator, and I'll I have that pull up on my other computer, but I'll take a screenshot and show you what I'm gonna do. I'm gonna do the same thing. I'm gonna input my variables, right? So we have values we can plug in, right? So I'm gonna do, instead of mu, I'm just gonna use u, k1, and that is supposed to equal 0.2. Yeah. And then u k2 is supposed to equal 0.1, right? So I'm just going back up here to these hints, right here to these hints. And then we also have the m1 is equal to just 1, m2 is equal to 2, that's easy. Theta is equal to 20 degrees, and I'm in degree mode. Is that everything? And so now if I go back down, oh, and G, of course, G is equal to 9.8. Yeah, that looks like everything. And so now I will type it in. So we'll do M1, M1, M2G cosine theta times u k1 minus u k2 over m 1 plus M2. Double checking to make sure I typed it in correctly. Perfect. Okay, and here I will put a screenshot in of what my calculator looks like. And so this is us. So using, oh man, you can tell my hands are tired. My handwriting is getting sloppy. Using hint 3 to check our equation. So UK1, I just typed in the numbers, and you can see, so hint 3 said we should have gotten 0.63, and we got 0.613. So I'm led to believe either that it's possible, or not either, but possibly that it's a typo on the hint on the worksheet, or because I had this do the calculation all at once rather than in pieces, so the instructor may have done the calculation in pieces, right? The instructor may have done this whole product right here, figured out what that was, then figured out what the fraction was, and then multiplied them together. And so, and if that professor only used 2 decimal places, and in fact, I can actually, let's check that. Okay. Okay. Yeah, so it's 0.41 times 0.03. Uh, I get even farther off. 3. Huh. Yeah, if I round it, I get actually even further off. So not entirely sure what's going on there. I assume, let's see if I change this to plus. Yeah, that doesn't make it closer. One. No. Anyway, yeah. So we get this. This is quite close. I would potentially put it down to actually, you know what? Maybe if we separate this out even a little bit more. So what if we get rid of that? What if we just do the numerator and just do the denominator? Right. And then we do, oh yeah, 18.4 times 0.1 divided by 3. No, I still get 0.613, so I'm not exactly sure. Oh, wait, this wouldn't be 4.1, this would be 4.2. Yeah, I'm not exactly sure how the in the hint how the professor got exactly that number. Um, Regardless, we are quite close. Um, and that does tell me that this calculation is correct. This is a lot of algebra, right? Like, yeah, like the professor said it was ugly, and it really is. This is a but what you end up with is a way to figure out any problem like this, right? That equation that we ended up with. Now, if you have two blocks on an inclined plane connected by a rope and they have different, actually, it doesn't matter if they have different frictions or not. Actually, if they have the same friction, notice that our fraction, the coefficients of friction would totally cancel each other out, and we just end up with this, um, which is kind of interesting. Um, Yeah. Uh, um, cool. All right. There's that. That's all I got in me. My brain is a little fried. Um, I need to focus on other stuff for a little while. But we got some good physics done today. Um, please submit your questions, and I will be back on Tuesday because there's still more of these to work on. I imagine I'm pretty positive that I will be doing my stream on Tuesday, unless something gets in the way. Like this last week, we've been dealing with the sick cat and stuff, so it's just been really hectic. And but with my new medication and stuff, I feel like it'll be a little bit easier for me to uh, to stick to my schedule. But yeah, I hope you all have a good rest of your weekend. Submit your questions, and I will be back Tuesday evening, 9 p.m. Pacific time, PST. Have such an awesome rest of your day.